Hey, welcome back, everyone. Here we are to section 10.3, and we are going to be talking about polar coordinates and eventually polar equations, and then some of the fun things we can do with them. So let's refresh our memories on what a polar coordinate is. Normally, what we have is a point x comma y, an ordered pair. And what we can do is we can actually transform it where instead of going in the x direction and the y direction, we actually turn at an angle and then from the origin go so far out in that angle. And just to illustrate that, I'm going to plot a couple of points here. So this is the zero angle. This is the positive direction. This is the negative angle direction. So this is a positive 5/4. So I'm going to start here and I'm going to go around to 5/4. And from the origin, I'm going to step out a distance of 1. So there's that point right there. You can see the circle, that's a unit circle, that's a radius of 2, radius of 3, 4, and 5, and so on. Now 3 pi is bigger than 2 pi. So actually I'm going to start here, I'm going to go around all the way once, and then I'm going to go another pi, and I'm going to go a distance of 1, 2. So that is going to be 2 comma 3 pi. Now here we have a negative angle, negative 2/3 pi is going to be 4/3 pi. And from there, I'm going to go a distance of 2. Now notice that was a negative angle there. Now for this one, we're going to go to 3/4. So we're going to turn all the way to here. Here's 3/4. And instead of going in the positive direction, I'm going to actually go in the negative direction, a distance of 3. So here's 3/4. So I'm going to go in this direction. So 1, 2, 3. So there is that point there. So let's mark this up just a little. This is A. This one was B. This one was C. And this one's D. So that's how polar coordinates work. And what we end up with is we're now going to view things in terms of r and theta instead of in terms of x and y, but we need a translation. We need to be able to go from one to the other. And you can see from this triangle here that the cosine of theta is x over r, which means x equals r cosine theta. And you can see that right there. Also, the sine of theta is y over r, which means y equals r sine theta, which is what we have here. Now you can also see the Pythagorean theorem here. X squared plus y squared equals r squared. There it is right there. You can also see that the tangent of theta is going to be y over x. So we're all covered there with these, and we're going to refer back to these often. These are going to be our main translation, especially when we're going from one to the other. And let's go ahead and do some conversions. So here we have a point that is there, and they want us to go from polar to Cartesian, meaning we want x and y only. Well, I know x is r, which is 2, cosine theta, I'm getting that from there, which is pi over 3. So this is going to be 2, and cosine of pi over 3 is 1/2. It's going to be 1. Now, before we get going on this too far, notice pi over 3, that's in quadrant 1. So I'm expecting both x and y to be positive in this case. Y is going to be r, which is 2 sine theta, which is pi over 3. This will be 2 times root 3 over 2. And you see the 2's reduce. So we end up with the ordered pair, 1 comma root 3. Notice both x and y are positive, so we are in quadrant 1. And root 3 is about 1.7 and change. So we are looking good. Now, for example 3, we're going to convert the point, and let's talk about where this point is and what that's going to look like. So I'm here. I'm at 1, -1. So 1, -1 is going to be this point right here. So we have a couple of ways to do this. First of all, I have a triangle that I'm going to end up with. And I know this is 1 and that's -1. So I need that hypotenuse to figure out what r is. So let's get r. And we have a choice, r can be positive or negative. I'm going to choose r to be positive since there's actually multiple ways to write the same point in Cartesian coordinates, which I won't get into right now. This is going to be x squared, which is 1 squared, plus -1 squared. And so my radius is going to be √2. Now I'm in quadrant 4, so I actually have a couple of options. They don't tell us what quadrant or any limits on theta as we're doing this. And so this is going to be -1/1, which is -1. And theta actually can be quite a few different things. That can be a -π/4 or 7π/4. So in actuality, we can write the same point 2 different ways. With a positive radius. Now we could write it 2 more ways with negative radii, but I'm not going to get into that right now. So there we are with the conversion. All right, let's talk about polar curves, meaning we're going to have actual equations where r is now a function of theta. Now what that means is, depending on the angle, so if I start here and as the angle changes, you can see the radius is changing. That's kind of what's happening here, is as theta is getting larger, r is changing. So r is now dependent on theta. So let's talk about this. What curve is represented by the polar equation r equals 2? Well, let's talk about that. R equals 2. If I square both sides, I'm there. And r squared is x squared plus y squared, in this case, equals 4. So that's going to be a circle centered at the origin with a radius of 2. 1, 2. And again, that's a radius of 2. Next up, example 5. Sketch the polar curve theta equals 1. So here, r was a constant. What happens when theta is a constant? Well, you can see it's going to be locked in at the exact same angle forever. And r can be anything it wants to be. So this is basically a straight line. I've actually already curved it. Now the angle here is a permanent 1 radian. So straight line with 1 radian. All right, let's get a little bit more complicated. This is when r is constant. This is when theta is a constant. And actually, we can do a little bit more work here. We'll leave it there. Sketch the curve r equals 2 cosine theta. All right, so what I've done is I've broken down a table for us. Now we could plot these points. I'd have to go a distance of √3 out and √2/2 and so on as we're doing this. But what I want to do instead is I want to convert this into Cartesian coordinates, like it asked me to do here. So I'm going to multiply both sides by r. And if we go back to our purple box here, do you see r cosine theta is x? And r squared is x squared plus y squared. So we end up with So we've converted it, but this isn't quite in a form that I'm as familiar with that I'd like to be. So what I'm going to do is I'm going to move the 2x to the other side. And I'm going to go ahead and complete the square. Take the 2, cut it in half, add it to both sides. So that's going to be +1, +1. So this factors into x minus 1 squared plus y squared equals 1. So this is a circle centered at the point 1, 0. So we are centered right here with a radius of 1. So this is going to be that circle right there. So it's just offset just a little bit more round. So that's what that is going to look like. All right. Example 7. Sketch the curve. Now we're going to sketch this 2 different ways. If I sketch it using r and theta, do you see that the smallest that is going to get is going to be -1, and -1 plus 1 is 0, and you can see that right there. That's at 3 pi over 2. And the largest this will be is when sine is equal to 1. That's going to be at pi over 2, and you can see at pi over 2, it's a distance of 2, 1 plus 1. So you can really see that there. And here, r is 0. So let's walk through how we translate this into this. We start out at angle 0. So this is angle theta equals 0. Sine of 0 is 0. So r is 1. And you can see that's the distance across there. Then as we go to pi over 2, sine of pi over 2 is 1. 1 plus 1 is 2. And you can see that's the height of this curve. So from here to here, it goes up to 2. And you can see that is analogous there. Next up, as we go from pi over 2 to pi, so from pi over 2 to pi, you can see it's decreasing here. Here. And then from pi to 3 pi over 2, you can see we're going to 0. We're going to hit 0. So you can see the little dimple there. And then from 3 pi over 2 to 2 pi, it increases a bit. So you can see the r is increasing out to 1 again, which is at 2 pi. So this shape here is called a cardioid. Because it kind of looks like a heart, I guess. So that's where that curve comes from. And again, you can really break this up into the pieces that you see here. So this is the curve here. I want to show you in your calculator how you would graph this. So what you would need to do is we would need to first of all verify that we are in that we are in radian mode. If you're in degree mode, this will not work. Next up, I'm going to go to mode again, and I see this line here. Right now, I put it into polar equations because that's what we're going to be doing. Normally, you're in functional notation, so when you hit y equals, you get y equals. But when we switch the mode, so there's parametric equations we could graph, but we're going to do polar equations. So now when I hit y equals, it brings in r. And r is going to be 1 plus the sine. And my theta is right there. Notice it's a theta now, not an x. And before I graph that, my window, I'm going to go from, theta is going to go from 0 to 2 pi, which is what we have. Small step size. X, I'm going to have go from -2 to 2. And y is also going to go from -1, excuse me, to 2. So when I graph this, you can see our beautiful cardioid, exactly the way that we just graphed that. All right, so we're going to sketch the curve y, or r equals cosine of 2 theta. Well, if we do an r versus theta, which is what we have here, r versus theta, we get this. And you can see from 0 to 2 pi, we actually end up with 2 full cycles. And that's because of the 2 theta. And in actuality, what's going to be happening with this graph, it's a little weird. When theta equals 0, r is at 1. So we're starting here. And you can see r is going to decrease and go down to 0. So that's 1. So that's this first one here. 2 is going to have a negative radius. So instead of going here, it's going to go downward. So there's 2. 3 is going to decrease back down to 0. 4 is now positive, so we're at 3 pi over 4, that's here. And so on. So you can see how this is drawn. Now this one is called a rose. And you can see how it's now, it was a negative, and now it's going to go positive, back down to 0, negative, all the way down. It's different, I know, but I can show you here and watch how it draws itself. So I'm going to make the window all ones now. -1, 1, -1, 1. And this we're going to change to cosine 2 theta, cosine. And normally I'm super careful of making sure that we're in radian mode, but we just checked it. And I want you to watch the direction. It's going to start here and it's going to go like this, exactly in that direction, all the way through to there. So here we go with the graph. See that? Isn't that cool? All right, let's bring some calculus into the mix. How do we find tangents of polar curves? No problem. Now I'm going to treat r is now a function of theta. So when we see this r here, we need to keep in mind that is still a function of theta. So when I do the derivative, I'm going to be doing product rule. So the derivative of x with respect to theta is going to be dr d theta cosine theta minus r sine theta. And the reason it's minus is because the derivative of cosine is negative sine. So that's minus r sine theta. Do the same thing with y, dr d theta sine of theta. This one's going to be plus because it's r cosine theta. And if we treat this like it's a parametric equation, up top we're going to end up with dr d theta cosine theta sine theta. Let's start again. I'll go here. So dy dx is going to be this one, dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. So that is our formula. That's it. All right, so now the cardioid that we just drew, we're going to say, find the slope of the tangent line when theta equals pi over 3. Now, before we jump into that, what I want to do is I want to point out that sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2, because we're going to use that a lot today, right now. All right, so let's find dr d theta, since we're going to have to use that quite a bit. So that's easy. That's just cosine theta. So now let's apply this. dy dx. dr d theta, which is cosine theta, times sine theta, plus r, which is this, times cosine theta, over dr d theta, which is cosine theta, times cosine theta, minus r, which is 1 plus sine theta, times sine theta. All right, so we're going to drop these into here. Let's see what we get. I'm just gonna call that cosine squared, 1/2 squared, minus sine of theta, sine of theta. I'll just keep it outside, that's fine. So 1 plus sine of theta is √3/2. Sine of 5/3 is √3/2. Now we got to clean that up. So let's get some algebra going on here, or some arithmetic here. √3/4 plus that's going to be 2 plus √3/4, 1/4, minus 2 plus √3/2 times √3/2. I'm going to multiply top and bottom by 4 to get rid of all those denominators. And that is going to give us √3 plus 2 √3 over 1 minus, that's going to be 2√3, 2√3 minus 3. Oh, that's just, wait, let me back up here. All right, let's back it up a little bit. So this is going to end up with √3 plus 1 over -1 minus √3. Let me clean all that up. And you'll notice in the bottom, I can factor out a -1, and I get √3 plus 1. And very nicely, this reduces. And you end up with -1. Yeah, you'll have to play around with that a little bit. But that is polar coordinates.